It is recording now, so you're on.
Hello, everybody. Thanks, Mike, for hosting and setting up this webinar. My name is Michael Mishko. I work for Cypress Semiconductor. I'm the marketing director over the Type-C and power delivery products. I've been with Cypress just over 2.5 years. Before Cypress, I was with other companies such as Microchip, US SMSC, On Semiconductor, Analog Devices, and Intel Corporation. So been around power, been around digital, been around a lot of these aspects for quite a long time. And it's actually nice to see some of these things coming closer together, power and digital in the Type-C and power delivery world. I'm talking to you from Phoenix, Arizona, where I reside. And happy to spend 1 hour with you. I planned a slide set that'll last about 1 hour, maybe a little shorter, and I think at the end we'll leave some room for some question and answer. So in the format of the slides, we'll spend a few minutes on terminology. There's a lot of confusion out there about what some of the key terms mean. So I think it's smart for us to start off with a good foundation and good solid understanding of the definitions. And then as we go through the slides, they'll make more sense. Throughout this slide deck, we're going to have an overview of the Type-C specification, power delivery specification. We'll also go through the Cypress products and services and solutions to help you design in, you and customers. We'll also talk a little bit about what we could do for a next step as far as customer workshops and take this material to an even deeper level and more technical level. So to start off on the terminology, Type-C or USB Type-C is a worldwide specification authored and sponsored by the USB-IF. So it's not a Cypress standard, as many of you probably already know, but Cypress is one of the leading authors. We participate in all the working groups to put together the material that's inside the specification, and that gives us the opportunity to be on the leading edge to develop solutions in a quick time to fashion. So the Type-C spec is about connectors, cables, and wires. It's, in my opinion, about 90% mechanical in nature. It talks about a new 2.4 millimeter plug and receptacle, 22 pins in the plug, 24 pins in the receptacle. The plug is flippable or twistable, if you will. The cable, since it's also a C to C cable, same plug on both ends of the cable, means it's reversible. So the end user doesn't have to worry about plugging the A into the A and the B into the B anymore. So then what is power delivery? Sometimes we call power delivery PD or USB PD. This is the protocol and electrical specification that allows you to do the negotiation and the control and management of 100 watts of power on VBus. So with PD, you can raise the voltage on VBus up to 20 volts, and you can go above 3 amps to 5 amps with power delivery. Power delivery also allows you to do other things, such as identify different devices when they plug in and are connected to each other, so they can enumerate their identities and their capabilities. Power delivery also allows you to do advanced features such as alternate modes, and we'll talk about that in just a minute. Power delivery is communicated over the CC pin or configuration channel. The Type A and Type B connectors, I think many of us have. These are all around us. If you were to look through your briefcases and backpacks, you'd probably have at least 10, some of you maybe 20, of these Type A and Type B connectors. Provider and consumer. Provider is a VBus source. So this is the entity on the Type-C connection that is the owner of providing VBus power, the source of VBus power. A consumer is the other side of the VBus power delivery. They're the sink, the VBus sink. Downstream facing port is a data host. In the power delivery world, in the Type-C world, the downstream facing port also is the owner of the VBus sourcing role. The upstream facing port, or UFP, in the power delivery world is the data client. In the Type-C world, it's the data client and the VBus sink. Dual role port is a device that is set up so it can perform the DFP role, downstream facing port role, or the upstream facing port role. EMCA stands for electronically marked cable assembly. So the new Type-C cable that you can buy in the store now comes in 3 different varieties. The first one being a non-EMCA or non-marked cable. That is a Type-C to C cable that has no electronics inside. When you add a marker chip or an integrated circuit to one or both of the plugs, it becomes an EMCA, meaning it's electronically marked and it can report or enumerate its cable characteristics and identities. The third type of cable is also an EMCA, but they call it an active EMCA. An active EMCA combines not only the marker chip that we just mentioned, but it also combines with a retimer redriver on the superspeed signals. So that gives you the 3 different kinds of cables. One is a non-marked cable or non-EMCA. The second is the passive EMCA. The third is the active EMCA. Receptacle and plug. Receptacles are in DFPs and UFPs. You can think of them as the female version of the connector. The plugs are in cables. Overcurrent protection and overvoltage protection are now more common and frequent terms in the USB world with Type-C and power delivery, because as the VBus power goes up above 5 volts and above 1.5 amps, then OCP and OVP, overcurrent protection and overvoltage protection, become more common in the discussion. VCON. VCON is a new Type-C pin or bus wire that is used to power the marker chip inside the EMCA. It's 5 volts and typically 1 watt. VBus. VBus is a signal that's been around in legacy USB cables and connectors, typically 5 volts, but now with power delivery you can go above 5 volts up to 20 volts. The configuration channel, or CC pin, is where all of the VBus negotiation occurs. Even in the Type-C world, the CC wire is used for the VBus power negotiation. And in the PD world, USB PD world, it's used for all the power delivery protocols to do the different usages of power delivery. DPDN, these are legacy USB data connections that have come forward into the Type-C world as well, so they're for the USB 2 signals. TXP, TXN, RXP, RXN, these are also familiar to most in the USB cables as the USB 3 cables, or USB 3 data path. Now in the Type-C connectors and cables, you have 2 USB 3 paths. So there's actually 2 separate USB 3 paths used for standard normal USB data and also used for guest protocols such as DisplayPort. Sideband use, these are 2 pins that are used for non-USB communication. So when you first plug in your cable, you start in 5-volt USB. The SBU pins are not used in that mode. We call that the normal mode. They can be used later on after further negotiation in an alternate mode, oftentimes used as aux signals for DisplayPort or some kind of sideband bus for the alternate mode. Alternate modes. So we mentioned what normal mode is. Normal mode is USB. Alternate modes is when you negotiate out of USB mode and you turn over the conductors of the wire to guest protocols or other protocols such as DisplayPort or Thunderbolt are examples. The Type-C transceiver is a transmitter-receiver pair that is used to control the CC wire. So in the Type-C world, it's simplified. There's no PD packets. But in the power delivery world, all the power delivery packets are communicated and transmitted on the CC wire. RPs, RDs, and RAs. These are all termination resistors. You use these during your testing and validation to make sure your DFPs and UFPs and EMCAs are terminated correctly. But they also are used during runtime for negotiation, handshaking, and for role determination when you connect different devices on a Type-C connection. So RPs are pull-up resistors on both of the CC pins in the DFP. So you can see on the picture on the right, there's a DFP, and on CC1 and CC2, you have an RP resistor pulled up to some positive voltage. RDs are pull-down termination resistors in the UFP, and you see on the far right, on the CC1 and CC2 pins, there's an RD resistor for each of them pulled down to ground. RA resistors are located in EMCAs, both passive and active EMCAs, and they are pull-down resistors on the VCON pins. So you notice in the EMCA there's no termination on the CC pin, only on the two VCON pins. Okay, so why is Type-C and power delivery becoming so prevalent and so popular, and why is it so important? From a historical standpoint, the USB cable as a charging standard reached probably what you'd call ubiquitous status, meaning it's used everywhere. So you can see here some old devices. Hopefully none of us are still using Blackberries, but maybe we are. You see some smartphones, you see some cameras. They took advantage of the USB charging standard, especially as the VBus current was creeping up. It reached, with the BEAST battery charging 1.2 standard, it reached 7.5 watts. Outside of the USB-IF, many companies created their own charging standards using this cable, which even increased the power further than what the USB-IF had. So on the right, you see that there are press releases and mentions of mandates and governmental policies saying that the USB standard would be used for all charging standards. So China and Europe are two examples of these. And we're coming close to a 2017 date when the EU mandates that all phones and charging standards have a USB connector. So the USB-IF wanted to continue this momentum of the USB cable as a charging standard, and they wanted to make it available up to 100 watts. 100 watts allows you to do many other applications with VBus power, charging and delivering power, even up to notebook computers and PCs. So what is the difference between these different charging standards? Historically, as you've crept forward with different charging standards, everything has remained at 5 volts on VBus. Even the Type-C standard, if you incorporate it by itself with no PD, then you still are limited to 5 volts only. But you get up to 3 amps now, so 15 watts is what Type-C gets you. When you add power delivery, then you can start to change VBus voltage above 5 volts up to 20, and you can go above 3 amps up to 5 amps with power delivery protocol. There's a few different versions of power delivery out in the world today. For those of you who have followed since 2013, the power delivery momentum, The PD version 1.0 actually used A to B cables, and for the PD protocol it used BFSK, which was AC coupled onto VBus. That protocol, that version of the spec, 1.0, was actually officially deprecated in the latest PD 3.0 spec. That's why you see it hitting a brick wall. And the reason that spec had some difficulty is the A to B cables made it difficult and cumbersome to execute the roll swaps and the different PD-based protocols that were designed into the spec. The protocols were pretty amazing, so those haven't really changed. But with the start of PD 2.0 development, companies like Google and Apple were involved to create a new connector and cable standard called the Type-C standard, which really not only enabled all of the flexibility of the PD 1.0, but now it added some more data paths and some conductors in the cable to allow you to do even more than just power distribution and power roll negotiation. And we'll talk about that. You can see the PD 2.0 spec has been through a few revisions. The 1.1 revision was mainly driven by a lack of CC idle noise immunity that existed in the version 1.0. So Cypress worked with companies like Apple and others to prove that, levels such as 400 millivolt peak-to-peak noise rejection was required, and luckily Cypress was able to beat that with 680 millivolt peak-to-peak on CC idle noise with our PD controllers. Then when the 3.0 spec was kicked off and created, it was mainly driven by the need for a new power roll swap. So you'll see in one of the 6 new enhancements of the PD 3.0 spec there, the fast power roll swap. The fast power roll swap does not replace the VBus power roll swap, but it is available for a few applications such as charge-through dongles, battery-powered hosts that require the fast power roll swap to minimize the loss of VBus during a power roll swap. In addition to that fast power roll swap, some other enhancements were made, such as new PD power rules, which you can see was also incorporated into the revision 1.2 of the 2.0 spec. Some communication improvements, such as extended packet lengths on PD packets, extended power supply and battery capabilities that are reported from source to sink, so they can be more intelligent and more efficient in how they deliver power across the cable. The last thing that the spec added was hooks, if you will, are the ability for external specs to plug in as optional features, such as the firmware update spec and the authentication spec. So today the PD 2.0 and 3.0 are running in parallel. Right now there's no indication that the 2.0 spec will be end of life or hit the end of its road. So now a customer has a choice. They can either do 2.0, 3.0. The two protocols are backward compatible, if you will. They do talk to each other and interoperate. If a customer wants PD 3.0, Cypress is the first company that is demonstrating PD 3.0 solutions today based on our CCG3 and CCG4 products. So what is power delivery then? In my opinion, the name of the power delivery spec now almost becomes a misnomer, but I guess it's become popular enough that they keep the term. As I mentioned early on, it was just about VBus power, voltage and current negotiation. But now there's some other enhancements that are made available. Start of packet enumeration, SOP, SOP prime, and double prime. This is a way for hosts or DFPs and UFPs and EMCAs to identify each other, exchange capabilities and performance metrics. So you don't try and do something on the cable that you shouldn't do because one of your 3 entities of the port partners can't support it. We'll talk more about that. The third usage of power delivery is the roll swap negotiation and control. So in the Type-C world, you're very limited on what roles you can do and then you also have some unintended consequences of your role swaps in Type-C world. For example, the data role and the VBus power role are locked together in the Type-C world. So a DFP has to be both the data host and the VBus source, as well as the vCon source. The UFP has to be the data client and the VBus sync. You can't separate those roles, the data and the power role. In power delivery, as you see here, there's actually 3 versions of role swaps that are possible. The data role swap, which is used to switch the DFP and the UFP, or the data host and the data client. And independently, the power role swap can be done, which negotiates the role of the VBus source and the VBus sync. If the DFP, if it's not convenient for the DFP to do vCon, power vCon, it can ask the UFP to power vCon. And in each of these swaps, it's a request. It's not a mandate. So when you make the request, the swapping partner can either reject or accept these role swaps. So hopefully you can see there, and by the diagram on the right, you get all degrees of freedom with power delivery and role swaps. Alternate mode negotiation and control is the 4th use of the power delivery protocol. So you actually start in normal USB mode, then you negotiate into a alternate mode or a guest protocol. DisplayPort, Thunderbolt, MHL are some examples where you actually turn over the super speed path and the SBU lines for these other protocols to use. So if that's power delivery, then what is Type-C? As I mentioned before, Type-C is really a mechanical standard. It gives you pinouts, receptacles, plugs, and cables and wires that allows you to have the transport and the flexibility and the ease of use of the PD protocol. From a Cypress standpoint, as we go visit customers around the world, and we've helped most of them design in PD and Type-C products, we see all kinds of benefits of the Type-C standard. For example, the Type A and Type B interface that we've all either grown to love or hate, we've been using it, the connectors are too big. A lot of the applications today want to get slimmer and sleeker, and the connector size is a physical limitation to do that. Also, the A to B cables have a fixed plug orientation and fixed cable direction. So I think each of you would agree with me that every time you plug in a Type A or Type B cable, probably takes you on average 3 or 4 attempts to get that plug in there, because you got to wonder what the orientation is and line up the paddle cards, things like that. Another weakness of the Type A and Type B standard was it only carried USB protocols. I mean, some companies tried doing graphics over a USB cable, but that was still USB protocols. It was compressed video into USB packets. The limitation of 7.5 watts also limited how much power you could deliver over a Type A or Type B cable. So you can see the benefits here of the Type-C standard as it fixes all of those shortcomings. The slim 2.4 millimeter plug height, the reversible plug and cable direction, the ability to transport 10 gig USB as well as other guest protocols onto the cable, and the ability to do 100 watts at a pretty reasonable cost is quite compelling and powerful. So you can see in the picture in the bottom that it's kind of like all roads lead to Rome. Well, all connectors are heading towards Type-C. Power connectors, graphics connectors, and all of the legacy USB connectors. So you may wonder, and you may ask me, where do you find a USB opportunity? Well, wherever your customers are using any of these outline connectors, Type A's, Type B, USB, Thunderbolts, mini DPs, HDMIs, even barrel jacks, any of these are potential candidates to switch to the Type-C standard. I mean, you'd be amazed how many different types of customers I've met at trade shows and at workshops where they come in and say, yeah, I'm doing a camping headlight or headlamp for backpacking that we're switching to Type-C. Coffee makers, phones, cubicles, even cubicles. We've talked to cubicle customers where they're switching from a 110 AC power distribution between cubicles with power delivery type power transfer inside the cubicles. So you'd be amazed what types of applications are switching to Type-C. So my challenge to you is just go and do a query with your customer, which applications use these types of I/O connectors. And it may not be today, it may not be next month, but in time they'll most likely consider switching that to a Type-C connector. So this is the original problem statement driven by the power delivery standard. Too many cables to connect your computing device to a display and to storage. So this example shows you a notebook PC. So think of this in your house. So you probably don't do this in your work because you probably have a docking station. But when you unka-chunk out of your docking station and you go home to your house and you try and plug your notebook PC into a monitor, you have at least 3 cables. You have a power cable, you have a display cable, and if you're using a remote storage, you probably already have a data cable, a USB cable as well. So the power delivery standard tried to fix this with 1.0, but they only replaced 2 of the cables. Type-C actually replaced all 3 cables with one single, simple-to-use, flexible, yet powerful cable. So the Type-C cable now allows you to receive 100 watts of power from the wall plug through the monitor to charge your PC computer. Your PC computer is the graphics source, and it can do 4K graphics onto the screen. Your PC is also the USB host, and it can store and retrieve and back up data to the remote hard drive using the Type-C standard. So we call this the trifecta, 3 technologies on 1 cable. Power, display, and data all on 1 cable. Now, for those of you who are getting tired of lugging your big PC around, this use case also is applicable to smartphones. So for the longest time, smartphones have been plenty powerful and capable of producing 4K graphics and even doing high data transport, such as USB. But the micro B connector and the technology behind it and the specs around it were the preventative element of allowing you to use it as a PC. Now with the Type-C standard and with PD protocol, you could actually replace this picture of a PC and put a smartphone there. And now with a Bluetooth keyboard and a mouse, you can use your phone as a content creation rather than just a content consumption device. The market is adopting all kinds of Type-C and power delivery products. So this is just a high-level snapshot. I could probably fill 20 slides of applications that are in the market now. But you see all kinds of hosts up on the top, starting with Apple, and now all of the PC manufacturers are selling both commercial and consumer brands of their products with Type-C connectors using the PD protocol. As you can imagine, as you release hosts out on the market, you must have the accessories that go with them and connect to them. So you see power adapters and power banks, both by OEMs and also aftermarket brands on there. On the device side, such as docking stations and monitors and hard drives are also out there in the market. Smartphones and tablets all over the place. And to connect these devices and these hosts together, there's all kinds of cables, true C2C cables, but there's also what we call dongles or adapters that convert the new Type-C standard to the old legacy connectors. As the market's adopting more and more products, there is some concern out there about certification. In fact, if you were to Google something like I show you here, USB Type-C damage, you would find article after article about concerns of hosts and devices being damaged by uncertified Type-C cables. Google has a engineer that's kind of leading this effort, and he has all kinds of testing data, and he shows which cables are good and bad. Amazon also has followed suit with its policies, and it says they will ban any Type-C cables that are not fully spec compliant. Cypress takes certification very seriously. This graph shows you across the vertical axis the number of USB-IF test identification numbers, and across the horizontal axis these are company names. The colors in the vertical bars represent dates. The dates are USB-IF sponsored plug fests and interoperability events. And so you can see here that Cypress not only is the only company that goes to every single one of these, but at each one we either tie or have the most test IDs. I think there's maybe one time where we didn't have the most test IDs. But you can see here that Cypress goes to every one of these. We send multiple engineers, multiple platforms to test our solutions. And we do this because end customers will have to certify their products, and that will become much easier when the silicon vendor has their solution certified. So you may wonder, why does Cypress have so many? Because by product, by part number, by application, by function, you need to get a test ID. So every time you have some different features or a different Type-C function or different application layer attributes in your platform, those need to be tested and certified. Cypress is the first in USB Type-C solutions because we had the very first standalone PD controller released to the market, and it was the very first one certified by the USB-IF. We call this product CCG1. CC stands for Type-C controller, Generation 1. After CCG1, we needed a smaller footprint because a lot of the accessories and also the higher density applications such as smartphones and travel adapters, power adapters, they needed smaller packages, yet the same functionality. So CCG2 was created, and it's 3.2 millimeters squared. Now some of you might say, well, that's not true, it's not the smallest in the world. Any of the competition's parts that are smaller than these are not standalone PD controllers. They don't have a PD stack inside. They require an external MCU or FPGA to be able to handle the PD protocols. CCG4 announced on December 2015 the first two-port PD controller in the world. So as applications adopt Type-C connectors and add power delivery protocol, they typically start with one connector, but the second generation, third generation are adding 2 and 3 and 4 Type-C connectors to each application. So this device allows you, with a single PD controller chip, to control 2 Type-C connectors in that PD protocol. Shortly after, January 2016, our device with highest integration was announced, CCG3. Not only does it incorporate everything you need from a basic Type-C and PD spec standpoint, but it also incorporates many other features such as a crypto block, 20-volt high voltage power input, 20-volt differential current sense, a smart power switch so you can be powered from a V-bus or a 5 or 3.3 volt level system level voltage. It also has an SBU MUX as well as a billboard controller inside. We're also proud to be the first supplier of a PD hub. So there are Type-C hubs out there in the world, but they don't support power delivery protocol. so they're limited to 15 watts only, and only Type-C role negotiation. This hub, the HX3C, is a 5 gig USB hub. It has 2 ports of power delivery integrated in. It also has a billboard controller inside. So a single chip can allow you to do very easy docking and accessory and display type applications. Also very popular in VR, virtual reality applications, where you want to use the PD protocol to transmit data, power, and graphics from the display on your head to the power pack and the compute engine in a backpack or on a belt. Cypress products are programmable. You can program them in either of 3 ways. Programmability helps because the Type-C standard and power delivery standard keep changing with ECOs. And also, as we all know, our customer requirements change as well. So being able to be programmable allows you to make those quick changes without having to do a board spin or wait for a silicon change. You can use the Mini-Prog3 and the SWD inputs of the CCG products to program with a hex file. You can also use any of the 2 bootloaders. So we have a bootloader over I2C, where we've developed a host processor interface protocol on top of the I2C connection that allows you not only a bootloader capability, but an MCU can become the master controller, if you will, of the CCGX device. The CC bootloader is useful for applications that are not hosts and not connected to the internet, and the only access you have is the Type-C connector. So think of a power adapter, think of a cable, think of a power bank. So you can reprogram the flash inside the CCGX using the CC bootloader as well. Inside the CCG3 and CCG4 are 2 banks of 64 KB flash. The banks are identical typically in a production environment, but you use the 2 banks as a seamless and invisible update for the G3 and the G4 products. So you're executing code out of bank number 1, for example. You then program from an external host or even from the host itself, bank number 2. When it's certified and verified, then execution of bank number 2 becomes the active bank, and it is used for the new code that's running. Even the HX3C is programmable. So think of the HX3C in a docking station. So when you connect your PC, which is connected to the internet, it can go and get a signed certified driver or a firmware update from the internet. And then it uses USB, vendor-defined messages, to vendor-specific messages to program the HX3C. So that programs the hub, the billboard controller, and the 2 PD controllers inside the device. Cypress is proud to be the first supplier to produce a software development kit. So our EasyPD SDK allows you to use the familiar PSOC Creator IDE, develop your own system layer firmware on top of the PD stack. Writing in the familiar creator here, you can compile and build and create bootloadable projects. You can also use the design resource program to assign pins and functions and resources. In addition, you can use the schematic capture to create schematics around the PD controller. Then in the bottom left corner, you use the EasyPD configuration utility to program your application with your new code that you wrote in the SDK. And on the far right corner, bottom right corner, you use the EasyPD protocol analyzer to test, debug, and analyze to make sure that the device is operating the way you want it to on the PD, on the Type-C connection. So let's get a little lower in detail. I know that we're all engineers on this call, so let's build a block diagram together. Let's build the source block diagram. So in the diagram you see right now, you see a power source for VBus. You see a USB controller that's connected at at a minimum, it's connected to the USB 2 signals. I mean, if you weren't connected to those, it'd be hard to justify that you have a USB connection. They're connected, this oval shape with the blue circles in the middle is the Type-C receptacle, and the blue circles are the pins of the Type-C receptacle. So the first thing that the Type-C spec requires from a source block diagram is a FET, or some FETs, on the VBus signal. In the Type-C standard, the VBus signal is at 0 volts in an unconnected state. It's not at 5 volts. Traditionally, Type A connectors have had a hot 5 volts. Can't do that on a Type-C receptacle because sometimes you may get a host or a source connecting to a source either intentionally or unintentionally. So you have a FET to enable and disable VBus power. The next thing that the spec requires is pull-up resistors on CC1 and CC2 called RP resistors. These are used to identify this Type-C port as a source port, or DFP. The ability to measure analog voltage on CC1 and CC2 is also required so you can detect when a sink is connected to the Type-C port. So we draw in an ADC and an analog mux. The third thing the spec requires is the ability to use the CC pin pull-down characteristics from the device to detect the orientation of the plug. So remember, the plug can be plugged in upside up or upside down. So the DC characteristics with the pull-down resistors on CC1 and CC2 is how you detect the plug orientation. Then you use that information to correct for plug orientation. So you correct for plug orientation, meaning that you have to use the mux that just came into the picture on the bottom of the diagram to realign the superspeed data path when it's in the upside down configuration. You also use this information to apply VCON to the correct CC pin. So you notice the receptacle does not have a VCON pin because VCON has to be applied to either CC1 or CC2 when VCON is required. So therefore we draw a VCON source and a FET on both CC1 and CC2. The fourth thing that the spec requires is the ability to enable VBus and VCON. So now we need some kind of control block, state machine or MCU, that can turn on and off FETs for VBus and for VCON. It also is used to switch the mux for the superspeed data path on the plug orientation correction. The fifth thing the spec requires, or actually it's optional, but the source can dynamically adjust its value of RP, which indicates the VBus current limit. So connecting the control block to the RP resistors so you can change the value of those allows the source to advertise in the Type-C world, not in the PD world, in the Type-C world, what the VBus current limit is. The sixth thing the spec talks about is the ability to monitor and detect when a sink is detached. So similarly, we use the ADC and the mux to monitor when a sink is attached. We also look at those voltages continuously to distinguish when the sink detaches, because when it does so, we have to remove VBus and VCON power from those pins. The last statement is a conditional statement. This is where you're going to see the tie between the Type-C spec and the power delivery spec. If the source supports advanced functions such as power delivery or alternate modes, then a PD communication or transceiver is required. So I drew in there a DisplayPort source. You can see the graphic signals DP1 through 2, DP3 through 4 going through the mux, and they can be connected to the superspeed data path. You also see the DPOX 0 and 1 going through the SBU mux to the SBU pins. And you also see the hot plug detect signal that's connected to the control bus of this CC control block diagram, source block diagram. So if you support modes like this, the only way you can enter those modes is through PD negotiation. Therefore, you must have a PD transceiver receiver on both CC1 and CC2. So that's the source block diagram from a Type C standpoint. Let's do the same thing on the sync side. So we have a power sync on VBus now, and we have a device controller connected to USB 2. The spec requires RD resistors for a sync on CC1 and CC2. The ability to monitor VBus voltage is also required, and it's used in the state machine to leave the debounce state and enter the attached sync state. The sync can also optionally measure the available VBus current from the source. So it's optional, but if you don't incorporate this functionality in your sync or your UFP, then you cannot take advantage of the 1.5 or 3.0 amps that could be available on VBus because you don't know what source is going to be plugged into your sync. So it means that you're probably limited to 500 milliamps, sometimes 900 milliamps if you don't incorporate this step number 3. From a good news standpoint, all of the Cypress controllers do this for you automatically, so not a big deal when you design in Cypress. The ability then to communicate that current limit to the power sync is also required if you are monitoring and detecting those different current limits on VBus. The fourth thing the spec provides for is the use of a FET on the consumer path, consumer VBus path. You may argue that this is optional from the Type C spec perspective, but as Cypress has gone around and helped many customers design in, having a FET on the consumer path allows you to protect yourself from overvoltage and undervoltage scenarios that could come down the VBus wire. We also add the control block now that handles the current limit control, current limit communication, as well as the FET control. The ability to detect and establish the superspeed path routing is also something the sync does. So we don't add VCON from the sync side because the sync does not have to provide VCON power, but we do provide the MUX. If the device has superspeed USB designed in or alternate modes, then it needs a MUX inside. If the UFP only supports USB 2, then you can see from the diagram that the MUX is not required. Another conditional statement to finish off the sync block diagram: if you support advanced modes such as alternate modes, and I draw the DisplayPort sync here, which is the opposite side of what we had on the source, then you must have PD controllers to negotiate the alternate modes in the advanced functions. So that's the sync block diagram. We also talk about DRP, and don't worry, the DRP will go faster for those of you who are tired of creating block diagrams. The DRP, from a spec standpoint, the first thing it includes is the full DFP block diagram. So this is the DFP block diagram we drew 2 slides ago. The next thing it requires is the additional UFP elements. So we add in the VBus consumer path, we add in the voltage monitoring node, we add in the power sync and the iLimit communication path. We also add the RD resistors to the CC1 and CC2. Being able to control, I'll give you both of these at the same time, being able to turn on and off RDs, as well as switch back and forth between RPs and RDs, are the last required elements of the DRP block diagram. So you can imagine as a DRP can do both the source and the sync role, the DFP and the UFP role. It presents RPs on the CCs, and then it toggles to RDs. RPs, RDs, RPs, RDs. And that toggling nature of the RPs and RDs is what allows this application to connect as either the DFP or the UFP, depending on what's on the other end of the cable. Okay, let's tell you from a Cypress standpoint what our products incorporate, so you can help to decide and promote which products are best for each customer application. So you remember CCG2 is the smallest standalone PD controller. Therefore, it only has the bare minimum needed to do the DRP, the DFP, and the USB applications. So if I draw a blue box around the CCG2 elements, it has the control block, which for Cypress is an ARM CM0 MCU with flash, so it has 32 KB of flash. It has the two PD controllers, and it supports both PD2 and Power Delivery 2, all of the different revisions of PD2 and most of the PD3 standard. It has analog detection and analog muxing. It has the RPs and RDs, which are actually not discrete resistors. They're current sources inside the CCG2. But you'll notice the VCon FETs are not in CCG2 because not all applications require VCon FETs. So this allows us to be as small as possible and as cheap as possible for those applications. Also notice that the high voltage VBus FETs, the power sources and power sinks are not inside the Cypress controllers, as well as the muxes. The SBU mux and data muxes are not inside the CCG2. Okay, from a CCG3 standpoint, remember it's the standalone PD controller with the highest integration. So if I draw a block around what we incorporate there, we move to the right and we take in the VCon FETs. So we have one pair of VCon FETs. We also integrate the SBU mux, which is useful for some applications. Some applications only need the SBU mux. They don't need that data mux on the bottom. So this is perfect for some of those applications. Now remember, the CCG3 has more features than I'm showing you here. I'm just showing you from a PD and Type-C spec standpoint what's inside. All right, G4. So to just show you G4 and G4M, I have to back up from the block diagram maybe 10,000 feet. Now you see two Type-C receptacles. You see a single DisplayPort source for the two receptacles. You see a single USB host or device controller for both receptacles. And then you have individual VBus paths, super speed paths, and USB 2 paths, even individual CC1 and CC2 pins for each receptacle. So CCG4, think of it as CCG2 times 2, if you will. It does incorporate the VCon FETs, though. So it does have VCon FETs. It does have all the ADCs and the PD5s and the control needed to independently negotiate and control two Type-C ports with power delivery. Now we have a CCG4M. M stands for MUX. It has a 5 gig, one of the 5 gig crossbar switches and SBU muxes inside. You may ask why we didn't put two inside, because in the second generation of most platforms, when they add two connectors, there's one on the left side of the application, one on the right. So placing this device right next to one of the connectors allows you to use the integrated MUX. But to get to the far side, you probably need a MUX with a redriver retimer. So for that reason, we allow customers to choose their variety of favorite retimer redriver MUX, because they seem to get a little finicky and picky about that. So if you line up the products side by side, you can see G1, G2, G3 are all single port controllers. G2 or G4, G4M, and HX3C both have two PD ports. You can see that we've started to put more flash into our devices. Our first two had 32 KB of flash and 4 KB of SRAM. We were able to compact our stack and get a full featured stack certified in 32 KB. So that in itself is quite an effort. I think some of my competitors are saying they need 128 megabytes to do their PD stack. So, but allowing you to have two banks of 64 KB seemed to be a good customer request for G3 and G4. So beyond the 32 KB stack, you can now have somewhere around 25 to 30 KB of space to put in customer-specific features and other things you need to do. Then you have two banks of that, so you can do the seamless or invisible update, flash update of the devices. You'll notice that the G4, as mentioned, has two Type-C transceivers because it supports two connectors, as well as the HX3C. The alt mode MUX for DP is in the CCG4M, one copy of it. You can also see as you scroll down here, the G3 is the only one, or is G3 and HX3C are the only ones with billboard controllers. So that's useful from a dongle or docking or adapter perspective. Hardware authentication crypto block is inside the CCG3. Allows you to do up to 256 AES or SHA, as well as CRC. It has a true random number generator, as well as a non-random number generator, has a pseudo-random number generator and a true random number generator inside. VCon FETs, one pair in G3, two pairs in G4, but on the other devices it requires external VCon FETs. Notice that the CCG3 can drive 20-volt VBus NFETs or PFETs. So it has its own gate drivers inside, so the customer can choose either NFETs or PFETs for that 20-volt VBus path. The supply voltage, typically a 5-volt supply on all these devices, 3.3 to 5, but the G3 allows you to connect a 20-volt bus directly, 20-volt VBus directly to power the chip. Really nice for like dead battery detection and recovery. So you can see they're all sampling now, and we're very close to production launch on G3 and G4, G4M, and shortly after we'll have the HX3C in production as well. So you may be wondering, where do I use these devices? We've got this one slide here that shows you by application, by product, which is your first and second choice. So the green is the first choice, recommended probably because of cost and performance features, but the alternate solution is most likely what was designed in on the first generation of the product, so it's still viable, still shippable, still usable, but the green solution may offer you some advantages over the blue solution. So things like smartphones, also cables, and mobile power chargers. G2 is still the best solution for that. It has the best fit with AC to DC and DC to DC, as well as the SOC and the PMICs. And its size is just the best for EMCA cables. You can use G3 for mobile power chargers. Its cost is a little higher, but sometimes customers like those features and are willing to tolerate the cost. For PC power adapters, which are higher power, power banks, video dongles, multi-port adapters, Thunderbolt cables, hard drives, G3 looks like the best solution out there. But some of the blue bubbles, like I said, are also options that customers are selecting, and we've helped them design in. So some G4, some HX3C, and some G2. Notebook PCs, desktops, Thunderbolt PCs, tablets, two-in-ones. Two-in-ones are like a Surface type of a device that has a dockable keyboard that adds more functionality. So you can see G4 by far is the most popular there. It gives you the ability to do multiple ports, has a good size and good cost for that. It also incorporates the device policy manager that manages the two ports, so that's why it's popular there. But you can see that G3 and G2 has done some designs there and has captured some customer interest. From a docking and monitor and TV standpoint, as well as set-top box, USB hubs, these are all examples of where the HX3C becomes more compelling as a single chip solution, but we have done some G4 and G3 solutions in those spaces as well. Okay. Cypress offers development kits to not only help us as partners, sales and marketing and FAEs to demonstrate and show capabilities to our customers, but customers can also use these to do feasibility analysis and do internal demos and quick trade show demos of their applications. We've had some customers take these boards and just put them inside their own box and use them as a PD port inside their application for trade shows. Then when the customer actually designs their own product, they can reuse the same boards and they can reuse the same boards and use them as test boards to test their own application. So let's say they design a power adapter. They can use these boards as the different types of Type C and PD products and test their applications. The bottom right corner is what we call a protocol analyzer. So when Cypress started designing these products and introducing to customers, there were not validation and testing tools, so we had to create our own. So this EasyPD protocol analyzer kit is based on the PSOC 5, and you can see a Type C plug on one side, a Type C receptacle on the other. So it does an inline PD protocol kind of analyzer or sniffer, if you will. One example of these kits is the CCG3 kit, as I show you here. Cypress strategy on these boxes is PD in the box. So when the customer orders these and uses them, they get tested cables, tested power adapters, things that are known to work together. So out of the box, they get a good out-of-box experience, and they can do anything they want to from a PD standpoint with this kit. They can do host applications, device, power adapter. They can program and configure this board to act like any power delivery device they need. Close-up look at the board. Typically, they come with a base board, which you see on the left, and then a daughter card, which you see plugged in on the right. The base board doesn't typically change much from, say, G2 to G3 to G4. It gives you the ability to control one Type-C connector. So the Type-C connectors on the left-hand side, don't be amazed at how big it is. We put a mechanical strain relief over the top to keep the connector from lifting off the pads when customers are using it heavy duty. On the top side, there's a display port connector. This is a DPRX port. So you can connect your laptop computer to this port, and then it'll give you full DP alternate mode capability out the Type-C connector from a source standpoint. You also have a USB Type-B connector, so you can also connect that to your computer, and that'll give you USB 3.2 capability out the Type-C connector on the board. The green header is a VBus consumer power header. So when this board is acting as a sync, a VBus sync, you get the VBus connection on that terminal there, and that allows you to do some load testing if that's what you want to do. On the bottom edge of the baseboard is a black DC barrel connector. That's for the power adapter. And then the blue header next to it is actually used for, is actually directly tied to that connector as well, just in case you want to connect a bench level power supply to it. So just checking the clock here, we're at 5 minutes past the top of the hour. I think I've gone a little longer than I intended to do. So let me fast forward through some of these slides and get to my last slide, and then we'll open it up for questions.
Yes, Mike, you are a little long-winded, but we still appreciate you.
Okay, so Mike, I assume this slide deck is going to be made available to everyone. There's a lot more block diagrams and things that are inside the slide deck. The things you learned today are an overview of the Type-C spec, the PD spec overview. Hopefully you realize that Cypress has some market-leading products, services, and solutions. And then a way for you to get started with your customers using the kits and the reference designs. The one call to action that I would have for you is if you thought this high-level training was useful for you, we also offer workshops. So we offer a half day and a full day. The half day is a little bit more in depth than what we did today. We actually get the customers using the EasyPD protocol analyzer, and they get to learn how to see PD packets and understand them. The full day, we actually get into the configuration utility and the software development kit, learn how to write C code, and teach the customer how to write their own application firmware and use it in their board. So please consider over the next quarter or two or three the right time when you can get groups of 15 or 30 customers together, and we can come in and schedule a workshop and impress them even more.
Okay. So to all the engineers who are out there right now, I will be sending out a feedback form, and if you would please let me know, would you like to come in and have a full-day workshop on this, where we'll set up the hardware and the software? Now I'm going to start opening up the lines. Sorry, there's not just like one button I can flip everybody on and off, so I got to do it each individually. So hold on, almost getting there. Okay, that about does it. Everybody should be able to ask questions now. So do we have any questions out there?
This is Steve Walsh from over at ATI. I didn't have a question. I just wanted to say it was a great presentation. Thanks a lot, guys.
Hey, you know, this is the easiest way for us to do it for you, Steve. I mean, I kind of would like you to get in the car and drive for 20 hours, but, you know, I am a kind guy.
So I really enjoyed that. That was great. Thanks a lot, guys.
Now, for you, Steve, something to think about. If we do a day seminar, would you be interested in us WebExing it? We'll get you the boards that you need and stuff to play with, and then WebEx. You could join us by WebEx. Would that be something you'd want to do?
Possibly, yeah. Yeah.
Okay.
It would depend on the content, but yeah.
Okay. Anybody else out there?
I'm not sure if I heard someone else trying to ask questions. Oh, can you hear me?
Go ahead. I can hear you.
Okay. We have an application where we want a mobile device to be able to use DisplayPort as well as take in high-speed, high-power charging.
Okay.
It looks like the CCG3 kit that you had that kind of functionality, but it seemed like that wasn't what it was being advertised for in the slides that you gave. Could you speak a little to that particular use case?
Yeah, so that CCG3 board, the CY4531, has full DRP functionality, so it can do both UFP and DFP. It also offers either PD 2.0 or PD 3.0 full feature capability. So that means you can do exactly what you want to do. It sounded like you said you wanted it to be a USB device taking in up to 10 gig USB, and you also wanted it to be a VBus sync charging its battery at the same time. But then you wanted it to source DisplayPort out. Did I understand that correctly?
Yes, that's it precisely.
Yeah, so it can do that. When it's sourcing DisplayPort out, it can either do 2-lane DisplayPort, which uses one super speed USB channel, or 4-lane DisplayPort, which uses both super speed USB channels. In the 4-lane DisplayPort mode, you can only use USB 2 functionality because you're occupying both 10 gig or 5 gig USB channels for graphics.
Okay, thank you.
Yep.
Follow-up question to that. The CCG4M sounds like it has a lot of the functionality for that integrated directly into the one chip instead of having off-board components. When is that going to be available for use in products?
So customers are designing it in now on engineering sample base. It will be production launched here in about 4 weeks.
Okay,
so you can get samples of it now. There's reference design of material available. Some on the web, but if you don't find what you want on the web, let us know. We probably have it internally. It's just not on the web yet.
Okay, so it's just not ready for full production runs.
Correct. It's still on an ES part number when you sample it, but right now my design team says they don't see any silicon changes needed, but if they did one, any firmware the customer develops today would be forward compatible into that production part.
Awesome. Thank you.
Yep. Also footprint compatible, so no change in the footprint.
Okay, anybody else? Okay, guys, thank you very much for attending, and when we have the next topic, we'll let you know. But I will be sending out a feedback form. It is greatly appreciated if we get those forms back. It lets us and our management know that there is interest in this type of a format for a high-level overview of new technologies, and it also helps us figure out what we want to do for our next one. So thank you very much, guys, and everybody have a great day.
Thank you.